So coming back to the reflection in xy direction. So we had seen the reflection in when x is equals to y, that means 45 degrees angle or the slope was equals to 1. So now as we have studied about the projection, now the reflection can be thought of twice the projection. Here if 1 0 is projected here, we saw that it was equals to c into c by s, and so here in this point in the projection was c into c s, and the height of the length of this vector, this point was equals to here yes. So here you can see when I am projecting 1 0 on a theta line, and what will be its reflection? The same length what you are finding it here will be the length at this point, right? So so twice of that. So I have taken 2 times of c and c minus s, and the length of the vector remains same. So you can say that it is minus 1 0. That is nothing but you can expand this to c square minus 1 to c s. So its original length reflection, your length becomes 1 0. That length has to be maintained, and the projection is twice. This projection is equals to twice. I told you the your reflection image is that the image plus the original should be equals to your what? The 2 times of the projection, right? That is being this is your what 2 times of projection, and what is your this point x, that is minus the this one, what your image. So image what you are getting, that is minus x. So here what is image that you will get, that will be equals to 2c square minus 1, because x is what 0. That is I am finding the image as 2p minus x. So I know the projection here c into cs, and twice the projection it is. So to this I am getting twice the projection to cs and minus x. X is 1. This is your original 1 0. So you are getting this as image. So similarly for 0 1, what was this point? We had seen in the reflection it was s into this point was c s. So this was your projection. Twice the projection. So you can see here minus the minus x, that is x is your original image is 0 1. So the image is 2 times 2 cs minus 2x square minus 1. So your reflection matrix when the or the sorry, reflection matrix for this when it is projected on any of the theta line, it is 2c square minus 1 and 2cs yeah, this thing 2cs 2c square, this column, and the other column that is for 1 0 we have got that this is for 1 0 and this is for 0 1. So this can be understood when you study the projection first, and then you can look into this. So you can understand it better. Coming to, already we have done the projection. I have explained you the projection, and I have told you about the properties, reflection properties, and this properties also I have told you. So coming to some of the problems. So look at the problems using the geometrical representation of linear transformation. You can see here one of the problem asks this: what matrix has the effect of rotating every vector through 90 degrees? You have to rotate it through 90 degrees. So he has not mentioned the clockwise or anti-clockwise. We will always take it as an anti-clockwise as a basic, and then projecting the result onto the x-axis. So you are rotating it through a 90 degrees and then projecting it onto the x-axis. So here it is, you're projecting into the x-axis. What was the projection matrix for the x-axis? It was 1 0 0 0, and for 90 degrees you have to rotate it. It was 0 1 and minus 1 0, right? So you have to remember all that matrix, or you can just draw it and roughly, and then you can even find out the matrix. So here, and then what is asked next? What matrix represents the projection onto the x-axis followed by the projection onto the y-axis? That also you have to show. So here first term is matrix for 90 degrees rotation. You have 0, 1 and minus 1, 0. And matrix for projection onto the x-axis was 1, 0, 0, 0. First row 1, 0, second row 0, 0. And so you have to first find out the vector has to be rotated 90 degrees and then projecting the result onto the x-axis. So you have to write the projection first, even y-axis is written. So here you can see the vector is being rotated by 90 degrees. So it has been rotated by 90 degrees first. So here you will be having your vector written. So it is first, this is multiplied. So that means 90 degrees rotation is taking place first and then it is being projected onto the x-axis. So just multiply these two matrices, you will get it as 0, minus 1, 0, 0. So next is what was asked? Matrix for projection onto x-axis followed by the projection onto y-axis. So you know the matrix for projection into the y-axis is this matrix and x-axis is this. If you multiply, you are getting 0, 0, 0, 0. So what is that? That is nothing but projecting twice. You are projecting first to the x-axis and again then back to the y-axis. So you are getting it as 0, 0, 0 at the origin. You get it back. Okay. Next problem is verify directly from c square plus s square equals to 1 that reflection matrix satisfies h square equals to y. You have to satisfy that is reflection square is equals to identity matrix. So you know the property, trigonometric property, that cos square theta plus sin square theta is equals to 1. So instead of theta, we have taken it as phi here. So you have this property and you can write it as c square plus s square equals to 1, and you have to prove using this property. You have to prove this. So take h square, so h is this and h square, so multiply that, go on simplifying, and for after simplification you get this, and wherever you get, you simplify this. This is all. And here you are making use of the trigonometric property c square plus h square equals to 1, and using that property it comes to 1, 0, 0, 1. That is, this becomes 1 and this becomes this gets cancelled, this is 1 and this becomes cancelled, that becomes 0. You have an identity matrix. Okay, so that is being proved with that. Next is the matrix A is 2, 0, 0, 1, produces a stretching in the x direction, and draw the circle x square plus y square equals to 1 and sketch around it the points 2x, y that results from multiplication by A